Alright guys, the last time we ended with an example that was f of x is equal to 1 plus 3x minus 1/3 x cubed on the interval 0 to 3. Okay? Now that was dealing with a function and the area under a curve sort of in the abstract. But what I want to actually entertain right now is what would be the implications if that function had actually meant something. So what I've done here is I've replaced the x's with t's and called it v of t. What if a velocity function was that given function, and finding the area under the curve, what would it mean to find the area under the curve? Well, let's go ahead and just think about this in terms of a constant function, okay? And let's say that we have a constant function which runs like this, okay? And let's say that this right here represents time, and this represents velocity, okay? So the horizontal axis represents time, or t, and this represents velocity, v of t. Now, velocity is also a rate, okay? So if I want to find the area under that function from a to b, and let's, this is just a rectangle right here. We're not actually using any calculus right here. The area of a rectangle, if I want to actually find that area, is just one of those sides times the other one. So rate times time. Rate times time, therefore, is distance, and therefore that means that the area under the curve is the total distance traveled for any given velocity function. So if I were to take this velocity function and I were to actually find the area under the curve, and up to this point we've been doing it by Riemann sums and then finding our s of n and taking the limit as n goes to infinity. If that's the case, then integration or anti-differentiation or find the area under the curve of a velocity function will give you the distance traveled on that particular interval. And that should actually make sense considering the fact that integration is the inverse, right, of differentiation. Differentiation, we go from position to velocity. Anti-differentiation, we go from velocity to position, or basically the difference in positions, and you'll understand more about what that means later. The difference in positions, which is what we usually refer to as distance. Now, in the past, I have actually told you kind of the whole purpose of a derivative, right? The whole purpose of a derivative, okay, is to assess and evaluate rates of change, okay? Integration, which we are sort of on the cusp of starting right now, is a method of accumulation. Okay, and that should sort of make sense to us considering how we've led up to this point. If this were not a constant function, if this were actually a curve, as the 1 plus 3x minus 1/3 x cubed actually is, we recognize the fact that if we're going from A to B, right, we're dealing with an accumulation of more and more and more cross sections, right? We're trying to figure out a way to represent a cross section in general, okay, and then I want to add up an infinite number of infinitesimally thin cross sections. So it shouldn't be a surprise to us if integration by its very nature is a method of accumulation, that integration, or finding the area under a curve, will take us from velocity to distance, okay? That's sort of tacked on to the end of 5.1. We don't have to dwell on it all that much right now. We will actually come back to it here in a couple of sections where we'll actually be using that knowledge in order to basically do application problems in terms of integration and stuff like that. What I would like to do, however, is use that sort of as a springboard to talk about one more thing that I promised to talk about, and that is Riemann sums assessed by table, okay? When they give you a function, it winds up being really, really easy, especially if you have your calculator. You just plop it in, and you just have to be a little bit meticulous with the little bit meticulous with the notation, but it really shouldn't be all that big of a deal. But sometimes they don't give you the function itself. They describe a scenario and they give you a table of data. Now that actually makes a little more sense in terms of, if you're going to use this type of stuff to actually in sciences, where you're not given a formula necessarily up front. You actually have to work backwards from the data into an equation or a model or some sort of formula that actually models that mimics that data. So if I'm given data, I can still do the Riemann sums. It's just the fact that I don't have to actually evaluate those heights, those function values. They are actually given for me in the table. Okay? Now, the table shows the velocity of a remote-controlled toy car as it traveled down a hallway for 10 seconds. Okay? Notice that if I go from 0 to 10, I have 11 columns of data, right? Because it goes from 1 to 10, and then you have 0 as well. So basically, between these, there are, of course, 10 subintervals. One subinterval goes from 0 to 1. The next subinterval goes from 1 to 2. The third one goes from 2 to 3, and on and on and on. And the 10th one goes from 9 to 10. Estimate the distance traveled by the car using subintervals of length 1. Okay, and the method shown. Obviously, the method isn't shown. I sort of took this out of a worksheet packet and just sort of cut and pasted it onto this document right here. But we'll do it with the method that we actually know. Okay, so what we're going to do is let's use a left hand first. A left-hand Riemann sum is actually not going to be all that tough to do. We just have to know that. Remember when we were using a left-hand Riemann sum, like from maybe 0 to 4. It was 0, 1, 2, 3 that were the left-hand inputs that I would then plug in order to get the outputs, meaning the height of the rectangles. So basically, if we're doing the left-hand Riemann sum, then we're going to be interested in those values. Okay, and of course, if we use a right-hand Riemann sum, we're going to be interested in those values. Okay, so let's go ahead and do the left-hand Riemann sum. We know that the intervals are all 1 second apart. Okay, so we know that it's going to be basically the summation of all of those. I know that it's going to be length times, or height times width, and the width is always 1. So really, I just have to add up the heights. And so a left-hand Riemann sum is going to be 0 plus 6 plus 10 plus 16 plus 14 plus 12 plus 18 plus 22 plus 12 plus 4, right? Because those, and then of course multiply all of those times 1, and that is going to give us the left-hand Riemann sum. The right-hand Riemann sum is going to be basically scratch out the 0 right here, use all of these values, and then tack on the 2, right? Now those are in inches per second. So if I have 6 plus 10 plus 16 plus 14 plus 12 plus 18 plus 22 plus 12 plus 4 plus 2, then that winds up being the right-hand Riemann sum. And both of those are estimates because they're those approximations of the area under the velocity curve. Those wind up being estimates of the distance traveled, right? We don't have an equation, so we can't integrate. All we can do is use Riemann sums as a way of approximating those values. Okay. So basically, we just know that the right-hand Riemann sum is going to be 2 larger than the left-hand Riemann sum, and actually we can go ahead and add those up. So 6 plus 10. Plus 16 plus 14 plus 12 plus 18 plus 22 plus 12 plus 4 is 114. So the left-hand Riemann sum is 114. That means this one's going to be 116. So, I mean, probably split the difference and say it probably traveled 115 inches in those 10 seconds. Okay? And this is basically an example of two things. First of all, it's an example of how Riemann sums don't necessarily have to be used with an official equation, like a function that is given to you in analytic form. Riemann sums can be used from a table of data. Now, here's the reason why they ask that. You get a much better understanding of whether somebody knows what they're doing in calculus if you ask them the same kind of question from multiple perspectives. And if they just ask you to grind out methods of integration, you sort of miss out. You could have just, your teacher could have said, well, when you see these instructions, do these steps. And they have no idea whether you actually know what you're doing. But the more ways that they can ask the question, and the more ways they force you to answer the question, the better idea that they have of you actually knowing what you're doing. You actually are understanding calculus and not just mimicking methods that your teacher taught you. Let's go ahead and move on to another example of this. This is actually, we'll see how far we can actually get into this. This is actually an AP question, okay? And we'll go ahead and increase this and get rid of the answer key down at the bottom. So we have rocket A has positive velocity, v of t, okay, after being launched upward from an initial height of 0 feet at time t is equal to 0. Okay? Now, the velocity of the rocket is recorded for selected values of t over the intervals 0 to 80. Now notice that these all have uniform width. That's not always the case. Sometimes when you're given tabular data, it won't be of uniform width, and you'll have to sort of tweak your Riemann sum in order to get those areas of those rectangles very, very precisely. Okay. It says velocity. Okay, as shown in the table above. Now it says find the acceleration of rocket A over the time 0 to 80. Well, obviously going from velocity to acceleration, that has something to do with differentiation, okay? That's not really our topic right now, so let's actually move on to part B, which is actually a little bit better for us. Using correct units, explain the meaning of the integral from 10 to 70 of v of t dt in terms of the rocket's flight. Well, notice that it didn't do it for the entire thing, just from 10 to 70. So what does the integral from 10 to 70 of v of t mean? Or what is the area under the curve, under the velocity function's curve from 10 to 70 mean? Well, what it means is that is the total distance traveled from time t is equal to 10 to time t is equal to 70. Because you're basically accumulating velocity cross sections, and that gives you distance. Okay. Then it says use a midpoint Riemann sum with 3 subintervals of equal length to approximate it. Well, I know if I'm going from 10 to 70, my midpoint, if I want 3 subintervals, I go from 10 to 30, 30 to 50, and 50 to 70. Now that means that my midpoint is here, here, and here. Okay? So if I want to actually do that, I know that it's going to be the width, or the delta x, of each of these is going to be 20. Okay? And then I'm going to take the outputs for v of t that I don't get from a model, I don't get from an equation, I actually get from the table, and it's 22 plus 35 plus 44, and whatever that is, and we can go ahead and do that, plus 35 plus 44, and then multiply that by 20, and that winds up being 2020. Right? And all you did was they had data points. So I mean, you can actually graph these data points. And so 0, 10, 20, 30, 40, 50, 60, 70, 80. Okay, let me go ahead and push this up so you can actually see it. And so what they did is they gave you at 0, let's see, 10, 20, 30, 40, 50. Okay, at 0, the data point was 5. At 10, the data point was 14. At 20, the data point was 22. At 30, it was 29. At 40, it was 35. At 50, it was 40. At 60, it was 44. At 70, it was 47 and then 49. So I mean, you could sort of, you know, estimate the fact that it kind of curves up like this. But here's the thing: you weren't asked to actually draw the curve that is basically, you know, that would actually match those points. You're simply asked for those areas, okay? And you were asked for the midpoint here at 30, actually at 20, sorry, at 20. You're asked for the midpoint output here at 40 and the midpoint output here at 60, okay? And that right there is going to give you an approximate area under whatever the actual curve is. But you weren't using the formula, you weren't using the function, you were simply using data points. So it actually winds up being much, much easier. And a lot of people are hesitant because they're like, is it really that easy? Yeah, it really is that easy. It takes a little bit of getting used to because you're like, well, this is a calculus question and they're just asking me to crunch numbers. But they're asking you to crunch numbers because they're actually trying to get at whether you understand this conceptually, on top of the fact that approximation is a big theme in calculus anyway, for a number of reasons, some of which I've already discussed with you. In the next video, I'm going to try and figure out and kind of mop up the last few things that we need to talk about before we move on to 5.3. Again, if you have any questions, please feel free to email me. I would love to hear from you about any of those. Otherwise, be looking for the last video on 5.1 and 5.2, and then, of course, videos on 5.3, which is where we really get into the nitty-gritty details of integration and start actually grinding out some of that work.